Welcome back. In a previous video, we discussed intra-domain routing. The topic of this video is interdomain routing. The contents of this video are autonomous system. We are going to discuss issues that arise in interdomain routing, and we will learn a protocol that is used in interdomain routing called Border Gateway Protocol, or BGP for short. And then we will also discuss a related protocol that is used by routers inside an autonomous system called iBGP or interior BGP. By the end of this video, you would know what is an autonomous system. You would know what are the main issues in interdomain routing. And you will know how does BGP work. Actually, BGP is a vast topic. It's one of the most complex components of the internet. So we are going to discuss the basics here, and if you want to know more about BGP, you take some advanced course on computer networks. And then at the end, we will have a brief discussion of integration of interdomain routes and intradomain routes. The internet contains hundreds of thousands of networks. So the complexity of routing through such a huge network is managed by imposing hierarchies. The internet is organized as autonomous systems, each of which is controlled by a single administrative entity. So an autonomous system, right, it's also called a domain, right? So interdomain and intradomain, those terms come from this. An autonomous system contains first several networks, and then it corresponds to an independent administrative domain. Examples of autonomous systems are large company or university network, ISP network, and backbone network. Here is a diagram that shows two autonomous system 1 and autonomous system 2. And these autonomous systems are connected via this link that connects router R2 in autonomous system 1 to router R4 in autonomous system 2. The benefit of structuring the internet as a set of autonomous systems is that it gives us a scalable routing. It allows us to hierarchically aggregate the routing information in a large network. And it affords us by dividing the routing problem into two parts: routing within a single autonomous system and routing between autonomous systems. Autonomous system defines routing domain. So the kind of routing protocol that we use inside an autonomous system is called intra-domain routing protocol, or these are also called interior gateway protocol, IGP for short. And by structuring the internet as a set of autonomous systems allows us to decouple this problem of routing within an autonomous system and routing between autonomous systems. And so each autonomous system can now select its own routing protocol, right? So this, for example, might use ISIS, and this autonomous system might use OSPF. And the routes that are learned, for example, within this autonomous system 1 could be propagated by this router R2 to this router R4 in autonomous system 2, and vice versa. So this router R4 can propagate the routes learned inside autonomous system 2 to this router in autonomous system 1. And these routers then disseminate the route that they learned about the other autonomous system within their own autonomous systems. And for this to work, we have to have an interdomain routing protocol, right, which is an internet-wide standard. Interdomain routing is very different from intradomain routing. because in the case of interdomain routing, the routing decisions are to be based on policies rather than numerical metrics that we had been working with in the case of intra-domain routing. And these policies are derived from financial and business considerations. And furthermore, what adds to this complexity is that these policies are often confidential. Consider this diagram. It shows several autonomous systems, several ISPs. There's one here, another one here, another one there. And then there is this small corporation, another autonomous system, this large corporation, another one large corporation. And then there are some autonomous systems that are backbone service providers. And then there is a provider consumer relationship that exists between these autonomous systems. So, for example, this large corporation here is the consumer, and this backbone service provider is the provider of service. Similarly, this consumer IP provides services to small corporation. And so, what sort of complicates routing here is that these policies are based on financial considerations. So typically a consumer is going to pay uh, to the provider some money. So there is a money flow from corporation to the backbone provider, right? And similarly to this other one. And this money flow happens regardless of the direction of traffic, right? So this corporation, for example, is going to give money to this provider whether the traffic is coming from the service provider to the corporation or the corporation is sending traffic somewhere else. And therefore there may be a situation, for example, where this corporation, let's say corporation A, and let's say this is service provider B, and this is another service provider, the blue one, let's call it C here. And so there may be a situation where, let's say, A prefers B for some reason. Maybe B charges less per unit of traffic as opposed to C. And so the policy, it could be that if there is a path to a destination through B, then I want to send my traffic through B. Otherwise, we send the traffic through C. And it may also specify that I don't want to carry traffic between B and C, because realize that the money flow is always towards the provider. And so if this corporation A, for example, starts carrying traffic from, let's say, this provider to B, then basically it's paying, right, for providing service to both of these providers. It's not gaining anything. The issue of confidentiality arises because these service providers are competitors of each other. B is a competitor of C, and these ISPs here may be competitor of each other. Then the second issue is of a scale. The backbone routers must be able to carry traffic to anywhere in the internet. And then there are hundreds of thousands of IP prefixes that exist. And this sheer scale of number of different network prefixes makes this problem hard. And then there is issue of trust. B might advertise some paths that may be erroneous or that may be malicious. So for example, if B wants to intercept the traffic that is going to, let's say, this prefix 185.7, it might just advertise that prefix to A, and then the traffic that originates in A will simply be transiting through B, and B may or may not actually forward those packets to C. And so by doing this, B may be launching some man in the middle attack, or simply be just dropping all the traffic that is going to go to this network prefix. And this is called BGP hijacking. There had been several high profile cases of BGP hijack. So in 2008, Pakistan decided to ban YouTube, and its telecom agency blocked all this YouTube traffic, but it also advertised the prefixes that were used by YouTube, and that basically got propagated over internet. And as a result, all the traffic that was supposed to go to YouTube started coming to Pakistan, and basically you couldn't access YouTube servers, and I think it went on for 2 hours. Okay, so now we are back to that diagram that we saw a little while ago. So here we are going to understand a little bit more about the service providers. So there are service providers that mainly provide service to individuals or small businesses. And so here is one example. So this consumer ISP, for example, these ones. And these service providers connect to backbone providers, right? So here are some backbone providers. And these backbone service providers interconnect these service providers, and they also can provide connectivity to large corporations. And they are also called tier 1 or T1 service providers. And these consumer ISPs that connect to consumers or small businesses directly, they are actually tier 3 service provider. And there is also tier 2 service provider. And tier 2 service provider typically connects to a backbone service provider and then might provide services to several tier 3 ISPs, right? So this is another tier 3 ISP, and so on. So this a small corporation would pay to consumer ISP. This also pays to the backbone provider, and this pays to these two backbone providers, and so on, right? These consumer IPs probably one of these three in this case, they provide money too, so they have to get connectivity from one of these backbone service providers. So I don't know which one to, so but in any case they give money to maybe to this one, and so on. However, these tier 1 service providers don't pay anyone, so they own the network, right? And these are typically large networks, countrywide networks, and they connect with other tier 1 service providers at what is called peering point, and there is no money exchange between these tier 1 service providers. So basically traffic flows from any one tier 1 service provider to any other tier 1 service provider for free, and these are also called internet exchange points, or IXPs for short. At this point, I want to make it clear that this is a highly simplified picture of the internet. The relationship between autonomous systems in the internet is quite complex. In our discussion of interdomain routing, we will assume that the internet is an arbitrarily interconnected set of autonomous systems. Before we move on, we are going to define a few terms. The first term we're going to define is local traffic. We call a traffic local traffic if it originates inside an autonomous system or it's going to terminate within an autonomous system. And a traffic is called transit traffic when the traffic passes through an autonomous system. So suppose we have an autonomous system, and if traffic originates inside, some host or some node and goes outside, then it's local traffic. And a traffic that is going to terminate on some node inside this autonomous system, it's also local traffic. Note that we may have a situation that a traffic originates and then terminates inside, but that's really not a problem that is related to interdomain routing. And so it could be like that. And then transit traffic is the traffic that passes through an autonomous system. So this traffic neither originated nor is going to terminate inside this autonomous system. So might have originated somewhere outside here, it's going to go somewhere there. So it comes inside and then it transits through this autonomous system and then exits. Right, so this is transit traffic. Now we are going to classify autonomous systems into three categories: stub AS, multi-homed AS, and transit AS. A stub AS is an AS that has only one single connection to one other autonomous system. Right, so here is an example of stub AS. And since it has connection to only one other autonomous system, it can only carry local traffic. And then there is multi-homed autonomous system. So these are autonomous systems that have connections to more than one autonomous system, like this large corporation over here. So it has connection to this backbone network shown in blue, and then there is another one here that's in front in white. And so these are autonomous systems. As I said, they have multiple connections, but they don't carry transit traffic. And as I explained before, if they carry transit traffic, they are paying for the traffic that is neither originating inside this autonomous system nor is terminating here. And then there are transit ASs. These ASs have connections to more than one other AS, and they are designed to carry both transit and local traffic. So examples are this consumer ISP, right? So it's a transit AS. It carries traffic originating in this small corporation AS, maybe taking to somewhere else, or traffic that originated somewhere else to this one, and then it may have its own local traffic. And these are also transit AS, these backbone service providers. The goal of interdomain routing is to find any loop free path to the destination, and this is called reachability. And so by reachability we mean that we can reach network N through some autonomous system X. And so the reason that in the case of interdomain routing we are concerned only with reachability rather than optimality is that the autonomous systems are independent. So the cost metric in one autonomous system is probably meaningless in some other autonomous system. And therefore, when we find anything that is, even close to optimal, that is, considered a great achievement. So we can't really hope for optimality, but we only worry about reachability. Now we are going to discuss the basics of border gateway protocol. So every autonomous system has one or more routers through which traffic enters or leaves the autonomous system. And these routers are called border gateways or border routers. Then each autonomous system has one or more BGP speaker routers, and these are the routers that advertise local networks. They also advertise other reachable networks in the case of transit autonomous systems, and they give path information. Note that these BGP speakers need not be the same routers as border gateways. Right? So there may be some other routers inside autonomous system, but in generally BGP speakers are also the border routers. In this example, routers A, D, and E are border routers. BGP route announcements are very different from what we studied in intra-domain routing protocols. In the case of BGP, it advertises complete path as the routes. For example, when AS1 advertises route to, let us see, 128.96 network, then it's going to advertise AS1, AS2, and AS4. And therefore, BGP is also called path vector routing protocol. Here is another example. So here we have 3 autonomous systems, and this middle one is a transit, and these are ISPs. And so let's consider this network prefix C. So this is going to be advertised by this ISP as this network prefix C. It's going to be reachable through this autonomous system 3, and you're going to reach C via this router R3A. And so this is the advertisement that will be sent from let's say these are BGP speakers, the ones at the border. So R3A is going to send that to R2C. In the next hop, so the announcement is going to be the network prefix C is reachable via AS2 followed by AS3, right? So AS2 followed by AS3. And then this is going to be reachable through this router R2A, which is this one, because it's going to advertise this to the next autonomous system, right? So that's its advertisement. And then this autonomous system AS1 is going to advertise this route as the prefix C, right? It's going to be reachable via AS2 and AS3 and router R1A, because now it's R1A is going to send it to R2A, right? And so that's going to be the announcement, right? That's going to reach this network A. The case of another network, right? So suppose this ISP decides to advertise it like that, and so it takes different form, right? So it's still advertisement for network prefix C, still going through the same autonomous systems AS3, AS2, AS3, and then AS2, AS3, but the routers change. So in this case, to reach C, right, in this autonomous system 1, it's going to be sent to R1B. Now R1B is going to send it to R2B, and then it's going to go to R3B and so on. So what is shown here as the thick dashed lines is the route propagation, and this arrow shows the traffic propagation, right? So the packets from B are going to go to C via this route, and then packets from this network are going to go to C via this route. BGP also prevents loops. And to see why this is important, let's consider this example of this prefix 128.96. Now, AS1 learns of this prefix from AS2. Now, suppose AS1 then propagates it to AS3, right? And then AS3 propagates that to AS2, right? So this is the direction of route announcement. Then when there is a packet for this network that arrives at AS2, AS2 is going to forward to AS3 because it learned from AS3 of this path. Now AS3 learned of this prefix from AS1, so it's going to forward it to AS1. AS1 is then, because it learned from AS2, it's going to forward it to AS2, and it's going to continue being forwarded in this loop. BGP prevents this loop by enumerating full path in its announcements. And so in this case of this prefix 128.96, it's going to propagate this AS4, AS2, AS1, and AS3. And so when suppose AS3 had sent this announcement to AS2, now AS2 is going to recognize that its identifier appears in this path, and therefore it's not going to add this announcement that it received from S3, and that basically breaks this loop. However, to make that happen, these identifiers of autonomous systems must be unique, and to ensure that these autonomous system numbers are unique, they are assigned by regional internet registries. Initially they were only 16-bit numbers, but in 2009 they were extended to 32-bit numbers. When links fail or policies change, BGP withdraws the previously announced routes by sending update packets, and these update packets contain withdrawn routes advertisements. One thing to note is that BGP packets are sent using TCP, unlike what we have seen before, and like flooding, for example. So because it sends its packets over TCP, and we have not studied TCP as yet, but we all see that TCP provides reliable end-to-end delivery, and therefore it does not really send the route announcements again and again. So it only sends keep alive messages, basically saying that I am here, right? So these are short messages that a BGP speaker will keep sending, and if these keep alive messages stop coming after some timeout period, then the other BGP speakers that learned routes from this particular BGP speaker will discard the routes that they learned from this BGP speaker that stopped sending these keep alive messages. Now we are going to briefly look at some basic policies. The relationship between autonomous systems could be one of these three kinds. Could be a provider consumer relationship, could be consumer provider relationship, could be peer relationship. So let's say we have these autonomous systems, and let's call this one A and this one B, C, D, and E. And so these are tier 1 service providers, these are tier 2 service providers, and these are, let's say, tier 3 service providers. And so this is E is a provider for D, A is provider for B, B is customer of A, right? Then B is provider for C, C is customer of B. Similarly, C here is customer of D as well. So C is a multi-homing autonomous system. And then B and D are peers. A and E are peers as well, right? So these are these basic, three basic relationships. I recall that money flows from top to bottom, right? Like that. So C pays to B and D, B pays to A, D pays to E. A to B is a provider consumer relationship. So a policy for A would be to advertise all the routes that it knows to B and all the routes that it learns from B to everyone else. The next is consumer provider relationship. In this case, a policy would be that let's focus on B to A relationship. So B will advertise its own prefixes and the routes it has learned from its customers to A. And in turn, it will also advertise the routes that it learned from A to its customers F and C. And then there is also another consumer provider relationship, let's say C to both B and D. In this case, C will advertise its prefixes to both B and D, but it will not advertise the routes it learned from B to D or the routes it learned from D to B, because then it would be acting like a transit AS, and it's going to pay to these providers, and we have discussed it before as well. And the third is peer relationship. So let's just focus on these B to D and D to B relationship. So in this case, the policy would be that B would advertise the routes it learned from its customers, namely F and C to D. And D will do the same. So it's going to advertise the routes it learned from its customers C and G to B. Recall that there is no money exchange here, right? So B, and D don't pay each other for transit of traffic from one to other autonomous system. However, B is not going to advertise the routes that it learned from its provider to D, because in that case, it's going to be transiting traffic for A to D. So that's not what it's going to do. And similarly, D will not advertise the routes it learned from E to B. Here is an example that would help in clarifying the policies that we discussed in the previous slide. So there are 4 autonomous systems, AS1 through AS4. And what we had been saying as a provider is labeled here as transit. So AS2 is customer of AS1 and AS1 is provider to AS2, or AS1 provides transit to AS2. And then there are peering relationships as well. So AS2 is peer of AS3 and AS3 is peer of AS4. So let's say that there's some traffic that arrives at AS2 from this network, and it's supposed to be sent to B, some host in B. Now the routes are going to be advertised from these autonomous systems to AS1. So AS3 is going to advertise route to B to AS1. AS4 is also going to do the same. And AS2 being customer of AS1 is going to advertise routes to B and C both to AS2. Now AS2 knows about both B and C, but it's going to advertise only its own prefixes to B. It's not going to advertise C to B, because in that case it's going to act like a transit. So it's going to advertise here only its own route. So it's going to advertise A, right, to B. And similarly, AS3 is going to advertise about B to AS1 and also about B to AS2. And so when AS2 has to send some traffic to B, it's not going to, it could reach B either via AS1 or it could use this peer connection. And because it does not have to pay for this peer connection, it's going to prefer this route, right? So it's going to just send it directly to S3. However, if S2 has to send a traffic to C, then it has to go through S2 and then eventually to C. In the beginning of this video, we discussed that we divide the routing problem into intra and interdomain routing so that the routing remains scalable. And so at the end, we have to be able to integrate these two routes that we learn, the one within an autonomous system and then the other one between autonomous systems. And so to illustrate this, we are going to work with this example that is shown here. So this autonomous system has 5 routers as shown here. A, E, and D are border gateways, and then B and C are some interior routers. The interior routers run a protocol called iBGP, or I for interior BGP. In addition to the intra-domain, one of the intra-domain routing protocols that we learned before, right? So it could be ISIS, or it could be OSPF, or it could be RIP. And these border routers, we're going to assume that these are the BGP speakers in this example, right? So they run this BGP that we talked about, right? So we were referring to that as BGP, but now we have to distinguish, and so we call this exterior BGP or eBGP. Since the interior routers know how to reach all the routers inside an AS, including these border routers, to be able to reach any other network. Let's say that we have another autonomous system and this IP prefix 12.5.5 is in this other autonomous system that's reachable via this border router A. Then for B to be able to route anything to this prefix, all it needs to know is how to reach A, and then A will then forward it to F, and from F it's going to be forwarded inside this network. This table contains the routes learned using BGP. So these are all interdomain routes, and these routes are learned using some interior gateway protocol. And this example is for router B. So all these networks 12.5.5 and 128.16 are reachable through A, right? So these networks are somewhere here. To reach this prefix 18.0, the traffic has to be sent to E, and to reach 128.34, the traffic has to be sent to D. And B has learned the paths to all the routers inside this autonomous system using some IGP. And this is the table that B is currently using. So to send anything to router A, it just sends directly. To send to C, again C is directly connected to sends to C directly. Then to send to D, it takes this path BCD instead of ABC, this example. And to send traffic to E, it takes this path B to C to E. And so to merge these two tables, it's rather straightforward. So what B is going to do is to send traffic to this prefix, right? It knows that to send to this prefix, it has to send to E, and it can reach E through C. So all it does is it sends this traffic with this destination to C. That's all it does. And similarly for 12.5.5, it's supposed to be sent to A. It's directly connected to it, so it's going to just send it to A. For the third prefix 128.34, it's going to be sent to D. For D, it prefers this path through C, so it sends this to C. And then lastly 128.69 sends to A. We saw that internet is arranged as a set of autonomous systems, where an autonomous system is a set of networks under the control of a single administrative entity. And we also learned that each autonomous system is assigned a unique autonomous system number. Interdomain routing is a term that refers to routing between different autonomous systems. We divide the routing problem into two parts: interdomain routing and intra-domain routing, and this division is crucial for scalability. We also saw that BGP advertises paths, and therefore it's also called path vector routing protocol, and is considered with reachability only. It is not concerned with optimality of routes. And we saw that there are two kinds of routers, right? When we talk about BGP border routers and speaker routers. BGP speaker routers that engage in interdomain route advertisements, and these speaker routers may or may not be border routers. And lastly, we saw that within an autonomous systems, routers use internal BGP to learn external routes, and then they combine it with the routes learned from some interior gateway protocol. So that's all in this video. See you next time.